Am I audible, guys? Guys, am I audible? Others? नहीं सुनाई पड़ रहा है क्या? Okay, I guess we are good to start then. This theme of Zoom looks cool. Like I just updated Zoom before the class. This UI looks better than the previous UI, right? Yeah, I mean they've added some more security features. But yeah, and this looks good. Okay, I think we are in a good state to start. Yeah, I'm so sorry for this, like preponing the class to 7, but I just had a meeting at 10, and that was like I got to know about it in the evening itself. Like, so that's why I couldn't help it. Otherwise, I would have like informed you much earlier, or maybe we could have worked out something else. But I guess we have a lot to cover. That's why I did not insist on starting at 8:30. We could have still done that and like done a short class, but we have a lot to cover, and that's why it's better to like have 3 hours classes every day. Okay. Can anyone summarize what we have done, what we had done yesterday? Should I pick up a name, or is anyone willing to volunteer? Not Drishan today. He has been summarizing for a long time now. Pradyum, can you summarize? So we actually had this virtual machine में mic नहीं चलता अच्छा. Karan, can you summarize maybe?
Sir, yesterday we discussed about using problems of subsequences. So the problems like were that it ended. We used that it ended at particular index. So we took decision that either we will include that or not include that. I remember that one.
Said is pretty much what we did. Wait, I'm audible, right, guys? Okay. Yeah, it lagged because I disconnected my VPN. Like I keep forgetting to disconnect my VPN, my office VPN. That's why as soon as I disconnected, there was like 10 seconds of lag. But I think we are good now. So we basically looked at 1D problems in ON square. So far, what we have done is we have primarily focused on 1D DPs, and we have looked at 1D DP problems in order n. So in all these, basically what we do is we try to, our sub problems are prefix arrays or suffix arrays. And essentially what we say is that if I am at a given index if I know if I know the outcome for an index greater than I or an index less than I, then I can compute for this particular index I using some logic. And we looked at a couple of decisions in order n dp, order n time. So one of them was if we could, when we were talking about sub arrays, we said that one of the primary, like the mission statement would typically be like dp of I will represent the sub array ending at I with that property. And we said that the decision in that case would typically be either a subarray of length 1 or more than 1, which means that I'm talking about the predecessor of this particular index. What can be the predecessor of it? It could either be I or it could be I minus 1. We just have two predecessors because it's a subarray. So if it is I, then we had a decision. If it is I minus 1, then we had a decision, right? So that was the predecessor in this case. And our mission statement was typically, we want to find out subarray ending at I, right? So that was one set of problems we looked at. And another type of problems that we looked at involved include exclude decisions, that you could either include this particular element at I, or you could not choose to exclude the element at this particular index. And depending on that you had a recurrence and a sub problem for J, which would be less than I. So that was the prefix suffix array order n dp, order n time 1d dp. Then in 1d dp itself, we looked at order n square time questions. So basically, the sub problem in that case is still continues to be prefix suffix arrays, and we looked at a couple of decisions yesterday. We looked at questions like word break, wherein our decision was, we looked at the eventual solution and we said that where is the point that you will place the first partition, right? So we will see a lot of decisions which will be similar to this. What is the first place where you would make a dent? That's basically the high level idea about this. And we looked at another type of decision which was mostly with subsequences. So in subsequences, our mission statement was similar to what we had for subarrays. We were trying to populate subsequences ending at a particular index I, and we said that the decision in this case would be that for a particular I, my predecessor could be any j less equals I, right? So I would have to consider all the j's less than I, and that's basically primarily the reason why these algorithms turned out to be n square, right? So essentially in order n square, we looked at two types of sub problems. This first partition sub problem, generalizing this, is basically we are saying that we are looking at the eventual solution and we are looking at the first element of the solution. That's basically what the decision. If you generalize this first partition decision, it is this decision, that we are looking at the first element of the solution, and that first element could be any of the elements from the array. Similarly, a specific example was word break, wherein we said that we will the first element of the solution basically means a word, right? So we could abstract it to a partition that we place at a particular, after a particular index I. Correct? So this decision is actually very important. How many of you understand this decision? Do you have questions in this decision? This decision, wherein the illustrative example we took was word break, but it will be generalizable to a lot of other problems. I will show you in n square DPs, in 2D DPs as well. We look at this, we take the decision a lot, many number of times. Today we will look at the knapsack problem. In knapsack also we will typically be using this decision also. Is this decision clear to everyone, the word break decision? Essentially, if you were to abstract it, what we are saying is that we are looking for the first element of the solution, and the decision is that that first element could be any of the elements from the given array or from the given search space, and then based on that we make a recurrence. Do you understand this? Like, how many of you understand? Can you acknowledge? Not for word break, whether and the generalizable decision as well, because this is a very important decision. We will see it being used in a lot number of questions. In 2D DPs, we use this decision many times. Others also, I'm assuming you understand, even if you're not acknowledging, which is, otherwise, if you are not understanding, please let me know. Yeah, Rishabh. So you understand, you were there when we did the word break problem, right? Rishabh, were you there when we did the word break problem yesterday? Yeah, okay. Then you will understand when we take more examples today. Okay. So you can bear. And the other type of decision is we are looking, when we are trying to extend a sequence, we are looking at its predecessor, right? So extending a sequence, we are looking at the predecessor. The decision is basically the predecessor could be, what is the predecessor or who is the predecessor if I were to extend the sequence at I at a given index. So subarrays, we said that the predecessor could only be I and I minus 1. For subsequences, we said the predecessor could be anything, any j less equals I. Do you understand this also? How many of you understand? Can you acknowledge? If you don't, can you? Because when we move to 2D DPs, these decisions, these two are the primary decisions which drive about 50 to 60% of DP questions. And I will show you again and again, these are fundamentally the decisions that we are using. We will, the sub problem might change. The sub problem will change from a prefix array to a 2D DP or a 3D DP, depending on the use case. But the decision essentially will be very similar to these two decisions. So it's very important that you understand these two decisions. We have done, like, I think quite a lot of questions on these two decisions. We will keep doing questions. So essentially, if there was any takeaway that you had to take from these couple of lectures that we have done on dynamic programming, it is this. Everything else is still fine. You can work out the details, but these are like the two essential decisions that you will encounter frequently. Okay, so let's do a couple of more order n square 1D DP questions, and then we will move on to order n square 2D DP questions. Let's do a couple of more 1D DP questions. So we were looking at the longest arithmetic sequence question, right? I will just share the question number with you guys. Yeah, I will paste the link only. This question. So for this question, again, the solution is similar. We are basically saying that the eventual arithmetic sequence, the longest arithmetic sequence, would end at one of the indices. It could end at index 0, it could end at index 1, it could end at index 2, and so on. It could end at index n minus 1. So what we will do is we will compute the longest arithmetic sequence ending at a given index I. So that's what we want to compute. We want to compute the longest arithmetic sequence ending at I. That's basically what we want to compute, and then we will take the max for all the i's, across all i's, LAS of I. That will be the result that we are looking for. So that's now when we are about to compute the longest arithmetic sequence ending at I, what is the decision? It's a subsequence, right? So one of the decisions could be what is its predecessor. So its predecessor could be any j less than I, correct? So let's take a j here, and let's say this is the predecessor. So what that means is that you will extend the longest arithmetic sequence ending at j by 1 and include the element I. Correct? So what is the criteria for I to be included in this chain? The common difference, the difference ai minus aj should be the same as the common difference for the chain ending at j, right? Because it's an arithmetic sequence. So we want to do that. So what chain can we extend? We can extend the chain ending at j for which the common difference is ai minus aj, right? So we want to extend the longest arithmetic sequence ending at j with common difference ai minus aj. That's what we want to do in order to obtain the longest arithmetic sequence at I. So we have to take this, we have to take the max of this for all the j's. Right? So what do we have to store then? For a given index, we should store the longest arithmetic sequence for all the common differences that it has encountered. Right? Do you understand this question, this part, that for an index j, I will have to store the longest arithmetic sequence ending at j with all the common differences that it has encountered. Right? And what is the best way to store that? You could use a map here. So where the key would be the key would be the common difference and the value would be the length of the chain. Right? So for this DP, we could use a vector of maps. And that's what we will do. This will be our DP vector. So let's see the code and you will get some essential aspects from this. So this is the question. My DP array will be a vector of maps. So I will just initialize it. This will be of length n. Right? And now what is the smallest? For any index, for the first index, for DP of 0, you don't have any common difference, right? So you will not have any map. The smallest will be empty. Now what you will do is, so there is no base case here. You will see why there is no base case here. Now what we will do is, we will start from 1. You could actually start from 0, but let's start from 1 for understanding. Now what I have to do is, I have to compute the longest arithmetic sequence ending at I, right? LAS ending at I. So I will iterate through all its possible predecessors. So all the possible predecessors would be from I minus 1 to 0, right? What will be the, let's compute the common difference, call it CD. So the CD for this would be AI minus AJ. Now there are two cases. One is, if for this predecessor, you don't get any sequence ending at J with this particular common difference. So if you don't get anything, this condition will hold. And what you have to do then, what is the length of this chain ending at I? It will be 2, right? So I will basically just the J and I. If that does not exist in the map, then it is just two elements, J and I, AJ and AI. So I will do that now. So for this common difference, whatever I have seen so far for this common difference and 2. If it exists, then I will extend it. So if it exists, then I will extend it. So how will I extend it? Whatever is this value dp of j cd, that means the longest chain ending at j with common difference cd, I will extend it by 1. Right? And essentially I will keep taking the maximum length. I can just initialize it to 1 also.
Sir, dp of ICD means the longest chain ending at I, right?
Longest chain ending at I with common difference cd.
So why are we making it 2 then? It is ending at j in the if condition.
No, in the if condition, we are checking if for the predecessor j, if there is no chain with common difference cd ending at j, then what is that sequence ending at I? It is just the jth element and the ith element. So what I am saying here is this case. You are at a given element I. So let's say you have a number 5 and this is 3 for this j. Now let's say before this there was no number like 1 or -1. You had no number with common with, so the chain ending at j with common difference 2 is empty, is 0 here. So there is no chain. So then what will I do? What is the chain ending at I with common difference 2? It is this and this element, right? That is the chain. So that's why I have said that if it is not present, then it is 2. If it is present, then I will just extend it. So whatever is the chain ending at 3 with common difference 2, let's say you had a 1 here. So you already have a chain. So dp of 3 common difference 2 would already be 2 here. So what I will do is ending at 5 will be just 1 more than whatever was there. So that's what I'm doing in that code. So that's basically what is there. And then I can just keep taking the maximum. Just run a couple of more test cases. Okay, is this solution clear to everyone? Why are we doing maximum? Because Karan, for that common difference we would have encountered, we could have already seen a sequence. So Karan's question is, why are we doing a maximum? You got it, right? Okay. So does everyone understand this solution? Can you acknowledge if you understand this, as well as how we arrived at this solution? So let's move on then. Let's do another question on order n. Let's try palindromic partition. I guess you did it. Did you guys? Yeah, I can show the code, Pranav. So let's try this question now. So this question, palindromic partition, you guys will be able to do. Can you tell me the decision? This is fairly simple. Word cut 2. Pranav, is it fine? Should I exit, stop the share, or should I? Okay. No problem. So I'm hoping that I don't discuss this question. Partition, you have to partition it such that every substring is a palindrome. Yeah, you guys will be able to do it, right? We can skip this. No questions in this. Yeah, I am also not, I did not plan to discuss this in the class. Okay. Let's do a gaming question. Let's try this. Stone game 3. Palindromic partition, by the way, has been asked by Uber a lot number of times. Uber का almost ये favorite question है, तो कर लेना एक बार आप लोग. Yeah, that is true. They are laying off people. Forget hiring. So let me give you a hint in this question. So these are what are called zero sum games. So this is a zero sum game question. It's not difficult if I give you a hint. Let's try to calculate the difference of scores for a sequence assuming the first player starts first. Yeah, let's discuss this after the class, Rishabh, okay? Yeah, I mean, we can discuss after the class. So what is the, so let's see, what is the problem? Now see, through this question, I will introduce another decision. Fairly straightforward. This is an explicit decision that is already given. What's there, what's given is you are given a pile of stones. So each stone has a value, right? So let's say you are given 1, 2, 3, 7. And let's say you are given more, 8, 9, 10, 11. These are the stones. Alice will start first. So both Alice and Bob are playing a game. Alice starts first. And what she can do is, she can take 1, 2, or 3 stones from this set. So she can either choose to take 1 stone, or she can choose to take 2 stones, or she can choose to take 3 stones. Right? And after that, so her score will be the sum of the values of the stones that she takes. So what is the decision with Alice? Say Alice can take 1 stone, 2 stones, or 3 stones. So if she takes 1 stone, she has a score of 1. If she takes 2 stones, she has a score of 1 plus 2. If she takes 3 stones, she has a score of 1 plus 2 plus 3, which is 6. After this, what happens is now Bob goes, and for Bob, when Alice takes first stone, for Bob, the problem boils down to this. Now Bob will play optimally from this sequence. If Alice takes this, for Bob, the problem boils down to this sequence. And if Alice takes down this, then for Bob, the problem is this. So this is a very straightforward decision that the question already has given it to you, right? So Alice goes first. Alice can take this, this, or this. If she takes this, you are left with this sub problem and Bob as the player. If she takes this, you are left with this sub problem and Bob as the player. If she takes this, you are left with this sub problem and Bob as the player. Right? And then again, you can repeat the same thing for Bob also. So Bob can now take 1, 2, or 3 here. So if Bob takes 1, you are left with 3, 7, 8, 9, 10, 11 with Alice as the first player. If he takes 2, then you are left with 7, 8, 9, 10, 11 with Alice as the player. If Bob takes 3, then you are left with 9, 10, 11 with Bob as the Alice as the player. And Bob has accumulated 3 points here. 3 plus 7, 10 points, and 3 plus 7 plus 8, 18 points. Right? Do you understand this? This is how the game will work. So what is the sub problem in this case? It's a very simple question, right? The sub problem in this case is a suffix array and a player. Correct? Right? How many of you understand this? That the sub problem, the decision is very straightforward. It's given in the question. Like we don't have to think anything with respect to the decision. But once the decision, you know the decision, you are left with a sub problem, which is a suffix array and a player name. Right? So you can do something like you can compute for every suffix array, you can compute the maximum that Alice can get if she starts first and the maximum Bob can get if he starts first. Right? So you can have two things. You could have a 2D DP where the second dimension only has 2 elements and the first dimension has n elements, and DP I0 will represent the maximum that Alice can get from ai to n minus 1. And dp of I1 could represent the maximum that Bob can get from ai to n minus 1. Right? And that now you can compute this, right? So dp of I0 is basically nothing but the minimum of 3 elements, 3 quantities, right? You have ai, plus what will you write here?
Minimum of dp.
Max of, yeah, I mean, it will be max, that's okay.
Yes, sir. The inside should be minimum, right?
Inside should be minimum, yes. I mean,
Minimum for Bob would be,
yeah. So what will be the recurrence? If Alice starts first, she can take 1, 2, or 3.
in a recurrence relation, that would be f of, if we are assuming it to be a function, f of I plus 1 and the remaining. If we are assuming it's Alice only taking the first. So
Yeah, I mean, so can you write that better? You can write this also, right? It will be, so whatever maximum Bob can get will be dp I plus 1, 1, right? So you can do summation ai plus 1 minus this. This is what Alice will get.
no, sir, I don't understand that.
So what we are saying here is that if Alice has 3 choices, right? Alice can take 1 element, 2 element, or 3 elements. If Alice takes 1 element, then we are left with this subarray I plus 1 to n minus 1, and Bob is going next. So Bob will try to play optimally and he will try to get whatever maximum that he can get. So whatever he can get can be stored in dp of I plus 1, 1, right?
Yeah.
So what will Alice get? She will get what remains. What remains from I plus 1 to n minus 1, that array, right? So it will be basically whatever summation you get from ai plus 1 to n. You could do aj, j is I plus 1 to n minus 1.
So
Whatever
wouldn't the memoization approach be more suitable for this question? Because that would be a top down would be a simple recurrence to write and a simple optimization with the
I mean,
2D
it's
array.
nearly the same, like it wouldn't matter so much.
Okay.
We can code both actually, that should be fine. Like I have not yet introduced memoization formally, but do you understand this relationship?
Yeah, I understand.
Others? Yeah. So what we are saying is, so you understand the dp this, right? You understand these two, right? So what is the decision that Alice can make? She can go for 1, she can go for 2, or she can go for 3. Let's say she goes for 1. What is the sub problem? If she goes for 1, she will get ai, correct? And she needs to get she will get something more. dp I0 is what Alice can get, right? So it will be, now what is dp I plus 1, 1? It is essentially the maximum that Bob can get if he starts from I plus 1 to n, correct? So what will Alice get when Bob plays optimally from I plus 1 and he tries to get the maximum that he can get? Alice will get whatever remains from the sequence. So you have a sequence from I plus 1 to n minus 1. Bob plays optimally and he gets some of them. What will Alice get? Alice will get the remaining. right? So that's what we have written here, that you could sum over all aj from I plus 1 to n minus 1 and subtract it from what Bob gets. That will be what Alice will get. Yeah, does this make sense? So you similarly you can write for 2 also. If Alice takes 2, she will get ai plus 1. And the sub problem that you will be left with will be a suffix array dp I from I plus 2. So now Bob will play optimally from I plus 2 to n minus 1. He will get something from I plus 2 to n minus 1. Whatever he gets, you can subtract I plus 2 to n minus 1. And whatever, that's basically what Alice will get. And similarly, you can write for 3, ai plus 1 plus ai plus 2. Right? Is this approach clear to everyone? Can I have acknowledgements if it is clear? The decision was very straightforward here. The decision was not really something that took us a lot of time. So these are all games that you play between alternating players, and you need to store typically a state for the player as well. And as well as basically in this case, the sub problems are suffix arrays. Now, I would not like to do it this way. I would try to do it better. So I don't want to get this thing of other players starting. What I want to do is, I will say that DPI stores the difference between the scores of player 1 and player 2 for sequence ai to n minus 1, assuming P1 goes first. This is the DP formulation. It's a little non-intuitive, but let's first try to understand this DP formulation, and let's try to define the recurrence if this is the DP formulation. So I'm saying DPI represents the difference between the scores of player 1 and player 2 for the sequence I to n minus 1, that is the suffix array, assuming P1 goes first. If this is the DP, can you tell me the recurrence? So let's see. Let's take a step back and let's see what we are trying to do here. You have some stones. Let's say DP0. No, they're not choosing consecutively. They are choosing alternatively. So Alice will choose one of either 2 or 2, 3 or 2, 3, 5. And then Bob will choose from the remaining sequence either 1, 2 or 3. Yeah, they're not choosing from consecutive indices, right? So Alice could choose, if Alice chooses only 2, then Bob is left with this sequence, the remaining. If Alice chooses 2 and 3, then Bob is left with this sequence. In terms of index, the first starting 1, 2 or 3 elements from the remaining sequence. The player is choosing either 1 or 2 or 3 elements from the remaining sequence. So let's see. I want to do something with the difference of scores to eliminate. So my goal is to eliminate the player dimension. I don't want the player dimension in my DP because it is making things a little complicated for me. So what I said is, then if you want to eliminate the player dimension, you could keep the difference between the scores. That's an idea that I give you. I mean, you can take it from me. If this is how we formulate the DP, can you tell me the recurrence? I can give you about 30 to 40 seconds to think on this. Or let's say, can you write the recurrence for this? So let's see. Let's say DP0 denotes the difference between the scores of Alice and Bob. So let's say difference between the scores of Alice and Bob, assuming Alice goes first.
Sir, can we do it like this? Well, if we know the difference, surely their sum would be the prefix sum, right? Suffix sum.
Yeah.
So we could get individual values.
Yeah, individual values we could get, but what is the recurrence?
So then it's basically the same, right? The previous recurrence that we wrote, we have two in different values for P1 and P2 up till I, and for I minus 1 we need to calculate, like for instead of storing it in 2 dimensions, we have stored the result in just 1 dimension. And the recurrence we wrote for the previous, using 2 dimension, we could use that only.
Yeah. I mean, whoever wins is fine. What is the recurrence? How will you write DP0 in terms of other DPs? DP I greater than 0. So see, DP0 is difference between Alice and Bob. So DP0 is Alice minus Bob, assuming Alice starts first. Difference between the scores of P1 and P2, assuming P1 starts first. So whoever is starting first is getting, is coming first in the difference also. That's basically the DP. So what is the choice that Alice has? Alice can take 2, 3 or 5, right? So let's take 2, 2, 3 and 2, 3, 5. So let's say Alice takes 2. If Alice takes 2, see her contribution is 2 from here. What will DP of 1 represent? I could compute DP of 1 as the difference between the scores of, what could DP1 represent? DP1 would represent the difference between the scores of Bob and Alice, assuming Bob goes first. right? So can I write this as 2 minus dp of 1? For this case, can I write this as 2 plus 3 minus dp of 1?
So what are we representing with the indices?
Exactly what's written in in English here. The difference between the scores of P1 and P2 for the sequence I to n minus 1, assuming P1 goes first.
Oh, okay.
So dp, if I want, what I'm saying is, if this will be dp2 and this will be dp3. So what will dp of 1 represent? The dp of 1 will represent the difference. I could make dp of 1 compute the difference between Bob and Alice's score, assuming Bob starts first. So whoever starts first in the game, I don't know who will start first, but I will simulate it, and whoever starts first, I will compute the difference of his score with the other player's score. And so then what is Alice's score overall? Her score is whatever she could get from this. Does this make sense?
So why are you subtracting this? Shouldn't you be adding only the contribution of Alice in the DP? DP1 would represent Bob minus Alice, right? So, but you should
only add Alice's contribution.
But you are maintaining you are having dp0 to be the difference between both these values, not the optimal value for Alice. dp0 would contain the optimal difference between Alice and Bob, right?
Yes. So what will that be? That will be, so dp of 0 will be, let's say Alice picks some elements. Let's say she picks this, she picks this, she picks this, she picks this, let's say. And let's say Bob picks the remaining, this, 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 this. So what is one way to write this? This basically is 2 plus, you could take the Bob's contribution first. So which is basically 3 plus 5 plus 9 plus 12 minus Alice's contribution, which is 5, no, not 5 here, 3 plus 7 plus 9, sorry.
7. Yeah.
3 plus 7 plus 3 plus 7 plus 10,
10
plus 12 minus 5.
So 14.
Yeah, why? Matlab, I'm just writing the sequence. I know the sum. Plus 12. हाँ, यहाँ 14 जाएगा. Plus 14 minus this. Right? You could write the total difference in this manner. That's what I have done here.
Okay.
Total Alice is basically this plus this. And total Bob is this.
Yeah. Okay, yeah.
किसी को समझ आया ये? How many of you have understood this? This is just a trick. Like it's very difficult to come up with this trick on your own. It's just a trick to, you could do the previous solution. Like if you are like getting bogged down by this solution, you could just do the previous solution. That is also order n. I mean, that's easier. But you could do this if you are really thinking, right? How many of you don't understand this? Can you tell me now and I can explain again? Yeah, Pradyum. So dp of 0 is, so what we are saying is we are simulating the game. Let's just simulate the game. Whoever, for a given sequence, what we are saying is for a given sequence from I to n minus 1, let's say whoever starts first, I want what dp of I will represent is whoever is starting first, that player's score minus the other player's score. I'm just saying this is the dp. Whoever starts first, dp of I will store his score minus the other player's score. That's what dp means. So now let's come to the question. The question is telling you to compute 0 to n minus 1 assuming Alice starts first. So let's say dp0 will give me the difference between Alice's score and Bob's score. So what is the choice that Alice has? She could either take 2 or 2, 3 or 2, 3, 5. If she takes 2, then from 1 to n minus 1, dp of 1 will represent what is the difference between Bob minus Alice if Bob starts first. So that is this. Right? So what is the total difference between Alice's score and Bob's score? Whatever Bob scored minus whatever Alice scored for the remaining sequence, this is there. And you have some numbers that Alice has gathered. So what is the total eventual Alice minus Bob? You will have to sum this with this and subtract it with this. Right? So you could do a minus here. And you will get Alice minus Bob. So this plus this is total Alice's score and this is Bob's score. So dp of 1 will represent this. Now, if you want to simulate one more level, let's see one more level. You will understand. Let's say Bob takes 3. Now Bob has 3 choices here as well. He can take 3, he can take 3, 5, he can take 3, 5, 7. So if he takes 3, you are left with dp of 2, which is basically from 5, this sequence. Whatever Alice gets, if she starts first, what will be Bob's total score? Bob's total score will be 3 minus this. Right? Because this is Alice minus Bob. And you have Bob here. So you want to sum this and this and subtract it with this. That will be the eventual score for Bob minus Alice for this sequence. Correct? Everyone understands this dp? Can I have acknowledgement if you understand? And if you don't, can I know? Yeah, it's just a trick. Like if you are not very comfortable with this, this is a general trick that you use for zero sum games. So this is what we called a zero sum minimax problem. These are minimax problems. If you have done a formal course on AI, they will introduce it more formally to you. These are minimax games. So you want to maximize something and minimize the other players. So here you are taking the maximum of Alice score and the minimum of Bob if you want Alice to win. So you could do some reading on minimax games. This is one of those minimax games. So this is one general trick that you could use for minimax games, wherein you use the difference to eliminate the player dimension. Just a trick that you could use. And this is how the DP would go for this particular problem. For other problems, we will do more problems on Minimax games. You will see different types of decisions. But the decision here is fairly simple. The recurrence is fairly simple. The DP formulation is something that is a little tricky. What the meaning of DPI means is. Correct? So now if you see, now you can do the regular DP exercise, which is basically if you have, what are you doing? You are doing for a given suffix, right? Yeah, now you think, how do we start filling the DP? When you are at a given index, you are using a suffix, right? Now when you would be, so you could see whether this is a DP or not. How? If you have, let's say this is 0 to n minus 1. If you go with one element, you will be left with 1 to n minus 1. If you go with two elements, you will be left with 2 to n minus 1. If you go with three elements, you will be left with 3 to n minus 1. Now here again, if you take one element, you will be left with 2 to n minus 1. Right? So aren't these overlapping subproblems? So you could, so now you could just store it once and use it. So what is the subproblem is a suffix array. So what is the smallest subproblem? Just the n minus 1, right? Size 1. And you could build for n minus 2, n minus 3, n minus 4, and so on. Correct? Everyone understands this flow? So we will dive straight away into the code if you understand this. So what will DP of n minus 1 be? DP of n minus 1 will be the difference between the players, the scores of player 1 minus player 2, or player 1 minus player 2, assuming player 1 starts first. So what will be that difference? That difference will be n minus 1. Right? N minus 1 will be his score and the other player's score will be 0. So the difference will be n minus 1. Right, Karan? Are you following? And then you could start from n minus 2. You have three cases here. You could take 1, 2, or 3. And depending on that, you could use DP n minus 1. Right? Shall we go into the code? Let's see the code for this question. So we want to fill from the smallest to the largest. This is n. Let's say the difference is 0. It does not matter. This will be stone value n minus 1. Right? Now you can start from n minus 2, go all the way to 0. You have three choices here. Take only one. So if you take only one, you will have DP of I. You can just initialize it to stone value I minus DP. If you take only this, you will be left with I plus 1. Correct? Take 2. So if you take 2, you can just take these two cases. So if I plus 2 is you could have, there are multiple ways you could get around this problem. I will show you a couple of ways. So you could have a temp and you could say that if it is less than n, then you could store dp of I plus 2 in this temp. Just initialize temp to 0. And now what you could do is, could say dp of I is max of whatever you have seen so far, and stone value I plus stone value I plus 1 minus temp. And this is the case when you take 3. So when you take 3, again you could have, only this is the case which will cause you problems. So let's complete this. There are neater ways of doing it. We will do that also. Just initialize it. So I plus 2 you will have to take or not take. I mean, now you could do dp of I is max of dpi stone value I plus stone value I plus 1. These two are guaranteed to exist. Only problem is with this. So you have stored that. This will actually go there. Minus temp. Right, and in the end you can return if dp0 is, Alice will win if dp0 is positive, right? So you could return if dp0 is 0, you could return tie. Could return Alice, else you could return Bob. Let's do a couple of more restrictions. Does this make sense to everyone? Karan, does this make sense now? Do you understand?
Sir, if I plus 3 is less than n, then already I plus 2 is less than n, then where we put condition?
Where? Come again? If I plus, no, this is temp1. This is a different variable to store stone value of I plus 1. So if I plus 3 is less than n, then yes, you will have temp1 as stone value of I plus 2. But you will also have temp1 as stone value of I plus 2 if I plus 2 is also less than n, right? So that's why we have done this. Like if you are saying, why don't we keep it here? That should be enough, right? That's what you're saying, Ishan.
Yes.
Is this
But
correct?
acha, theek hai. Then that case will be there that it is the last element.
Yeah.
When I plus 2 is the last element.
When I plus 2 is the last element, you have missed initializing temp1. In this case, maybe it might not happen. Will it happen? It can still happen, right? Yeah, it can still. So when you are at the third index from the last, your I plus 2 will be less than n, but I plus 3 will not be less than n, will be greater equals n, right? So when you are at the third last element, take this example if you are confused. When you are here, you will miss out on initializing temp1 to 7. Right? If you put it here. Because I plus 3 will be greater equals n, so this will not become true and you have not initialized temp1 then. सही है ईशान? कर सकते हैं. We will do that. We will see memoization, don't worry. But generally it is better if you can do bottom up, like simpler. This is very
In a previous question, I think we made a helper function which had the DP array as an argument.
in the previous question.
No, not in the previous question. I don't remember which question it was, but we did recursion and one argument.
Word break 2, that was pure recursion. That was not DP, right? That part 2 of word break was pure recursion. Recursion, we were not, so that was not memoization actually. That was just pure recursion. We just used that DP, that DP array was just another array that was being passed as an argument. You will understand more when we do more questions on memoization. Okay, let's hold that question till then. Is this approach clear to everyone? Can I have acknowledgements so that we can move on? If it is not clear, I can explain again. Any part you don't understand? Karan, where are you facing difficulties in understanding? Which part? So few acknowledgements. I want more. Okay, sure. I want more acknowledgements before we can move on because we have about 40 of you. Okay. Okay, see the video. If you don't still understand, you can get back to me. But essentially, the essential crux is in the statement, this statement. That it is the difference between the scores of P1 and P2 if P1 goes first. This is a generic enough statement, right? So that's basically the. Okay, let's move on. Let's go to 2D DP now. So this is another question that I showed you. wherein the decision is quite explicit, right? Here the decision was very explicit that the decision is you can either take 1 or 2 or 3. The only problem was we just took the player keeps alternating. So we removed that player dimension by using the difference. That's how we remove the player dimension. So let's begin with 2D DP then finally. So in 2D DP, essentially our sub problem will be two-dimensional. What does that mean? That means that our sub problem space can be represented as a matrix. Now follow this very carefully. If our sub problem is of two dimensions, basically what does that mean? That basically means that you have two one-dimensional parameters in the sub problem. So you can represent the problem through two parameters, through two arguments which are one-dimensional. So this could be an array, this could be an array, or this could be. So then your 2D DP essentially becomes a that space of all sub problems of a two-dimensional DP is a 2D array or a matrix. And in the matrix, every cell contains the solution of one sub problem. So what does that mean? Let's say A1 was a argument of one dimension which can go up from 1 to n, and A2 was another argument which can go from 1 to n2. A1 can go from 1 to n1. So what are the possible values that this pair can take? That will be the space of all possible subproblems, right? So what are the possibilities? You could have 1 1, you could have 1 2, you could have 1 3, and so on till 1 and 2. Then you could have 2 1, so on till 2 and 2, right? And so on. Then you could have 3 1 3 2 3 and 2, 4 1 4 2 4 and 2. Similarly, till you could have n1 and 2. And this will, so these are all the subproblems of a two-dimensional problem. What we mean is if we have a problem wherein we have two dimensions to the problem, so your problem mathematically can be represented by two dimensions. A1 is one dimension and A2 is another dimension. Then whatever the range of values the first dimension can take into whatever range of values the second dimension can take is the space of all possible subproblems. And that space can be represented as a 2D matrix with one dimension of the matrix for the first dimension of the problem and the second dimension of the matrix for the second dimension of the problem. So this could go from 1 to n1 and this could go from 1 to n2. So now every cell of this matrix stores a subproblem, stores the solution of a subproblem. So 1 1, this matrix stores the solution to problem P11. This matrix stores the solution to problem P22. Or if you are going one indexing, then P33. This matrix stores the solution to problem Pn23 and 22. Okay, so we will see what this basically means through an example. Let's take a simple example to illustrate some essentials of this. let's take this question, 494. Quite simple, but let's take this. So let's follow along. You will get, I will illustrate a lot of essentials of 2D-DP through this example. So here what we are given is, we are given a list of numbers. This could be any list, 2, 3, 4, 5, 1. I don't know why I naturally tend to write numbers in increasing order. 7, let's take 4 again. You are given a sum. Let's say 11. You have to find the total number of ways you can combine these numbers to give us sum of 11. So the combination could be that before every number you could either place a plus or a minus. So this is one possible value of this entire expression. If you place a plus in all the, before all the numbers. कुछ नहीं किया अभी, खाली क्वेश्चन 494 पढ़ो आप. 494 स्टार्ट किया, ठीक है? अगर read that. Similarly, if you place a minus here, you could do a -2 plus 3 plus 4 minus 5 plus 1 minus 7 plus 4. This is one possible, another possible value of the expression. So you have to find how many of such expressions give you a sum of 11. Or give you a given sum. Okay? So let's look at the decision here. You are given a sequence, a 1D sequence, right? So for most of the 1D sequences, you typically try to apply a decision at the first element. So here, your decision could be that for the first element, you could either do a plus or you could do a minus, right? If you do a plus, what is the resulting subproblem? The resulting subproblem is that you have to, is this sequence, and you have to get a sum of 13 from this sequence. Whatever number of ways you can get a sum of 13 from this sequence, you can get a sum of
9.
Sum of 9 from the sequence. You can get a sum of 11 from the entire sequence, including 2, right? If you take, and the other is if you take a minus. If you take a minus here, then you are left with this sequence and a sum of 13 now, right? Sum of 13 to find. If you can find a sum of 13 from this sequence, then you will, all the possibilities that where you find a sum of 13 from this sequence, you will be able to get a sum of 11 from the original sequence if you put a minus, right? So what we have done is we have split the eventual solution into 2 parts, those parts that contain a +2 and those that contain a -2. Right? Is the decision clear to everyone? Is the decision clear to everyone? So if this is the decision, then what is the subproblem being represented by? The subproblem is essentially being represented by 2 things here. You have a sum that you want to find, and you have a sequence from where you have to find the sum, right? So now we say that this problem has two dimensions. It has an array and it has an integer. Right? So for these cases, now once you understand that you have basically two dimensions, the next thing that you should do is you should just draw out the matrix for this. There are two dimensions here. You have a 1D suffix array as one dimension, and you have an integer as another dimension, right? So a 1D suffix array as one dimension and an integer as another dimension. So let's draw the matrix for this. Let's try to understand. So what are the possible values for the 1D subarray, for the 1D suffix array? It could be the entire array. It could be the array from 1 to n-1. It could be the array from 2 to n-1. It could be the array from 3 to n-1. It could be the array containing only the last element, n-1. So this is the dimension for the suffix array. What is the dimension for the sum? So you have a range that the sum can go, right? It can go from, what is the range? Minus summation ai to plus summation ai. Right? So one value is this, the next value is minus summation ai plus 1. The next value is, then you will have a 0 somewhere, then you will have 1, then you will have 2. These are the dimensions. So this is the total space of all sub problems of this problem. Right? Do you understand this first? This space of sub problems at an intuitive level, what this is meaning? Okay, if you understand this, then now let's look at the recurrence. The next thing we will do is, this is step 1, draw out the matrix. So define the range for both the dimensions of the sub problem and draw the matrix. That's the first step you do after you have made the decision and you have formulated a recurrence. So those two things remain from the previous. So make a decision and formulate a recurrence. So both of them remain as it is. The next step that you do once you have a recurrence is draw the matrix. So work out the ranges of both the dimensions and draw the matrix of this type. The next step that you should do is now simulate the recurrence on the matrix. So let's see what simulation of the recurrence on this matrix actually means. Let's write down the recurrence first. The recurrence is that dp of 0, the recurrence is that if you have two choices for the first, if you take plus, if you take minus. If you take plus, you are left with a suffix array and a sum, correct? And if you take a minus, you are left with another suffix array with some other sum. So you want to find a bigger suffix array here. So see one observation in this recurrence. You have a bigger suffix array here. This is, let me use a different color. this is a bigger suffix array. This is the smaller suffix array. Correct? So what does that mean? That means in order to formulate or get an answer for the bigger suffix array, you would need the value for the smaller suffix array. Right? So what does that mean? That means that if I am at a given suffix array size, let's say if I am at 3, if I have already pre-computed the values for all suffix arrays less than 3, which is here, because we are using a suffix array, I would be able to compute values for these. Do you understand this point? Others? How many of you understand this point? Yeah, Pranav. What I'm saying is, you understood this point that you have a bigger suffix array here and you are computing a bigger suffix array solution from a smaller suffix array solution, right? Are you able to see that in the recurrence, right? So now if you are able to see this, what does that mean? This is one dimension for the bigger suffix array. This is a bigger suffix array. This is more big. This is more big. As we go down, the size of the suffix array decreases, right? So when I want to fill for a given suffix array of a given size, if I have already computed the values for suffix arrays of size less than this particular size, then I can compute this, right? If all of these are green, then you can find values for this. How you want to find this, let's say. So this will basically be, you will copy from 2 some value. So if you are 0, let's say you will copy here for plus, and you will copy something from one of these cells for minus sum, right? And you will take the total combination, you will take the sum. Whatever is the possibilities for this, whatever are the possibilities for this, you will get the sum. Right? Do you see this, Pranav and others? So if you see this, this is a pattern that we see. The pattern is that for one dimension, the dimension which I can see that if I were to compute the, what do we store? Yeah, we will see. We could use any, this matrix is just a illustration. It's not an array that you think. So we will see how we can get around the problem of negative indexes. That's your question, right, Karan?
I'm asking what are we storing in the matrix?
So in the matrix, we are storing solution for a subproblem. So in this cell, we are storing the solution for suffix array from 1 to n-1 and this sum. Can you get how many possibilities are there to make this sum, this particular sum with this suffix array 1 to n-1? This cell is basically with suffix array n-2 to n-1. What are the number of ways you can get a sum of 0? It's just an extension of that one dimension case. We are populating for all possible subproblems, right? So all possible subproblems can be represented in this matrix. Right? So now I am getting down to the question of this, that I see this observation that when I am at a bigger suffix array, if I have the smaller suffix array's values pre-computed, I can find out the bigger suffix array. How? Let's say I'm at this index. So I want to find for this suffix array 2 to n-1, what are the number of ways to store some 0, right? So that will be, you can put a plus. If you put a plus, it will be a2. You will get a sum minus a2 remaining. So 0 minus A2. So let's say that is this cell. So 0 minus A2 with suffix array 3 to n minus 1, whatever are the number of possibilities for this, plus whatever are the number of possibilities for sum 0 plus A2 and suffix array 3 to n minus 1. So I will take these two values and sum them here. Right? That's the recurrence in this dimension, in this picture. That's how you are computing the recurrence. Right, Karan? Do you understand this? Yeah. So we are saying that we are using just the previous row. I mean, the previous smaller suffix arrays. So now I'm saying that, okay, if that is the case, then one strategy that I can use to populate this is if I populate it row wise. So if I populate it in this order, then there won't be any ambiguity, right? So I am trying to determine the order in which I will fill this array. So that's the question that I'm trying to answer, determining the order in which you will compute your sub problems. Here you can compute your sub problems in this manner. You will not have any issue, right? Because when you are at a given level, you only need the solutions of previous levels, which you have already computed. Is this order clear to everyone, that you can do away with this order? This is one of the most important aspects of 2D DP, determining the order in which you will compute the sub problems. How many of you understand this? Can you acknowledge? Because we will see questions wherein this is not the order in which you will compute the. So if you understand this, then we are good. Then basically what we will do is we will run two loops now. Now just we will run a loop from n minus 1 to 0. So that will basically be for this dimension. This will be the outer one, because we want to, when we are at a given I, we want all the values to be readily available for any j less than I. Right? And in this, I can go over all the sum values, which could be from minus ai to plus ai. And dpij will be a sub problem, and I can compute that. This will be the skeleton of my code. So that's what I have inferred. Karan, is this making sense? Pranav, is this making sense? Okay. Yeah, so that's basically the essence. So I will just summarize this before we move on. So for 2D DP or any general DP problem, even for one dimension, it's generally trivial to see. You will first come up with a decision. That decision, this is important and tough also at times. Once you come up with a decision, you will formulate your recurrence. Once you have a decision, it's easy to formulate the recurrence. Then you can have an understanding for your sub problem from the recurrence. Understand the sub problem that you have. Once you know that it's a 1D sub problem or it's a 2D sub problem, determine the order in which you will fill the sub problem space. And here we said that we will fill it in a row wise, where row is the row of the matrix is the size of the suffix array. And iske baad to you have, at a very high level, these are like the steps. Let's see the code for this, and we will try and understand more essential things. So how do we implement this DP array for this question? We have a two-dimensional subspace, a two-dimensional sub-problem space. So we could have a 2D vector, right? We could have a 2D vector for this, where the first dimension is for, let's say, the suffix array, and the second dimension is for the sum. We could have this. The only problem is that I cannot index by negative sums. So dpij will basically store the value, the number of ways you can compute the sum, number of ways to compute sum j from sequence a of I to n minus 1. Let's say this is how I am formulating the DP. Right now I have to, there is just one case that I have to take care of, which is the negative sum, right? I cannot index by negative sum. What can I do to get around that? Add everything, add a large number to this, right? Add some large number to this. That should be enough. And everything else remains the same. Let's see the code for this. We will understand a lot of essential more aspects of this, and then we can again come back to the discussion. So let's see. Now I know that this is a 2D DP. I will fill it row wise. This is the essence, filling it row wise. I will show you DPs wherein we have to fill diagonally. I will show you questions like that. And I know the recurrence. So it's given that the sum of elements will not exceed 1000. So I can just add 1000 to it, right? So let me declare the DP now. So 2 dimensions. The first dimension will be for the size of the array. So 0 to n minus 1. So this will be of size n. Let's have a vector because we've been using vector all the time. N. So this will be the first dimension. What is the second dimension? The second dimension is the sum dimension, right? So the sum will not exceed 1000. So your range will be from minus 1000 to plus 1000. So how many elements are there in minus 1000 to plus 1000? More than 2000, right? Let's take 2005 just to be safe. You can take exact also, 2001 or 2002, whatever will be the total number of elements. Plus 1 you will have to take. Let's just take 2005. And let's initialize everything to 0. Now, what is the base case here? So if we are filling it, now let's come back to this. Word break can be solved using diagonal filling also. Yeah, we can. Let's take the discussion after this question. So now you see this particular example. We are filling it row wise, right? So our smallest sub problem is this row. If I am able to compute, I will have to pre-fill this, hard code this, right? So that after that, for every other row, I can easily compute, right? Correct? So I can use an empty suffix array to be. So what I will do here is, first of all, do you understand this idea, this part that my sub problem is this final row? Karan, Pranav, do you understand this? Yeah, because I need to hard code values here, and then I can go on for sub problems, for bigger sub problems. So if you so what I will do here is, you could either hard code for the last row. So your last row is basically the just what all sum you can compute from the sequence, only this element, what for all the sums we want to compute. So let's see what we will do now. So the base case would be, I will fill it for the last row. So how do I fill it for the last row? I will go over all the sum values. Okay, so let me just go over from sum 0 to sum 2005. Does not matter. You can go for less. You can compute the sum also and iterate accordingly. I don't care. I will just go for all the values. For every this sum, dp of n minus 1 I is basically the number of ways you can make this. Right? Let's do it in this manner. Let's take this from minus 1000. This makes things easier. To 1000. So these are all the sum values, right? I will just keep adding 1000 to all the sums, right? So dp n minus 1 with this sum is basically the number of ways you can make this sum, make I from only the suffix part. So what will that be? For the suffix part, you have only two cases, right? Minus an minus 1 and minus and plus an minus 1, right? So we will just take care of those two cases here, that if I is minus an minus 1, then dp of n minus 1 I, so it's I will just store that in I plus 1000. That will be 1, right? If I is a n minus 1, then also I will store it as 1. Base case समझ आया सबको? Otherwise it is 0 and I have already initialized it to 0. How many of you understood the base case? Can you acknowledge? Pranav, sorry, Karan, does this make sense? So if this is the base case, now we can go over all the sub problems row wise. So I will, my top dimension will be the row. So from n minus 2 to 0, I will go. And my other dimension would be the sum. So my sum can go from minus 1000. You can actually compute the prefix sum and make your sum only go from that range, but it's okay. Like, let's do it this way. Correct. Now what is the case? You have a very simple case that dp of I j, I'm just shifting it by 1000. So that is basically the total number of ways you can make. So this will be, if you take a plus, so you have the decision here, take a plus or take a minus. So let's take a plus here. So if you take a plus, it will be dp of I minus 1, whatever remains basically, that subsequence. And what will be the sum? The sum will be, the sum expected will be j minus ai, right? I will just add 1000 to that because we are shifting everything by 1000, and take a minus. So dp of I j plus 1000 plus equals dp of I minus 1. If I take a minus, here. So the sum I will be left with is j plus an. I have to take care of the cases when it goes beyond, right? So I just have to take care of the cases when the sum goes beyond this. So I can actually change this. I will have to take these cases into consideration, that or the other way I could do it is I could have this as the minimum sum and the maximum sum. Then I would be for sure knowing that it would be. Let's do that. Let's just or I don't want to do that. Let's avoid it here. So how do I avoid this? Like, we can take care of the case. If this is getting less than 1000 or minus 1000, but that seems wrong. Yeah, what do we do here? Like, can anyone help me out? So I'm just thinking what will be the sum of the elements will not exceed 1000, it's given, right? So maximum you could get is from minus 1000 to plus 1000. What you could do is when you get a so other way you could do it is because the sum will not exceed 1000 when you are at a given sum, that what is the lowest that sum can get? It can get minus 1000, right? And if you subtract minus 1000 another 1000 from it, it can go up to minus 4000, minus 2000, right? So the other way I could do it is I could make this a 4000 size array, and then this will be fine. Will this work? Let's try. अरे यार nums array. So j minus nums I can go maximum minus 2000, right? Okay. So you will have to then If you are going minus 2000 to plus 2000, you will have to add a 2000 to everything. When minus 1000 minus minus 1000 minus 1000 minus 2000, so you want that to be 0. So you can do, this looks fine. Let's try a larger value, because you're going from minus 1000 to plus 1000, right? So, and a number can be maximum because the sum will not exceed 1000. The number अरे वो गलत तो है ही. Right. This is I plus 1, right? The sub problem is I plus 1 in that case, right? It will not be I minus 1. So that's what I've taken care of here. And the length of the array is positive, will not exceed 20. For this, why did it screw up? It's 2. Sum you want to make 1. This looks right. Yeah, this looks right. Why isn't this working for this case? If you were to see for all, will that be a problem? You will be saying that those, so you're saying that you either put a plus at this or you put a minus, whatever the number of ways you get. If you put a plus, that will be dp of I plus 1 j minus num psi. And if you take a minus, it will be j plus num psi, right? And so you are summing both of them. I don't think a plus equals is a problem here. Let's see this case. So you have to find sum of 1. For 0, dp of I0, only for 0 it will make this 1. Otherwise, for all the other sums, it will be 0. Now you are here, you want to make a sum of 1. You can take a plus. So if you take a plus here, you will get, so only for the sum as 1, this will be 0, right? So you will have 1 there. And for even for that sum, for j as 0, if you are, when you are iterating, you will get a For j as 1, you will get a 1 here and you will get a 0 here, because it will be 2 plus 2000. And if you take a minus 1 here, so you need a sum of if you take a minus 1, your sum will be basically for 1. For j as 1, you will get a 0 again, right? So for j as 1, you will get a 0, and for at any other time you will not get a 0, right? For j as minus 1 also you will get a 0, which is fine. The sum, so for j as minus 1, it becomes why will it be an issue? Yeah, that's what we are taking. So the only that it could be a 0. If you have a 0, you will not take a minus. That's the problem. Yeah, I got it. ये वाला जाएगा ये. राइट, अगर 0 नहीं होगा तो माइनस लगाओगे ना, 0 पे माइनस थोड़ी लगाओगे, 0 पे सिर्फ एक प्लस रहने दो.
सर हमें तो टोटल केसेस निकालने हैं, तो हम प्लस भी ले सकते हैं माइनस भी ले सकते हैं.
हाँ,
तो जो आप वो ऊपर कर रहे हो ना -1000 से 1000, वो पहले वाला लूप, तो उसके अंदर हमने पहली कंडीशन लगाई है i इक्वल टू -1 इंटू नम्स n -1.
राइट.
हाँ, फिर नीचे हमने लिखा है i इक्वल टू नम्स n -1. तो अगर नम्स n -1 0 हुआ तो उसके दो केसेस होंगे.
राइट.
हाँ, तो वो नीचे वाले के अंदर i इक्वल टू नम्स n -1 के अंदर प्लस इक्वल टू 1 कर दो. मतलब अगर वो 0 हुआ तो अगर वो वैल्यू दोबारा आ रही है तो फिर वो प्लस इक्वल टू 1 होगा ना, मतलब ऊपर.
हाँ, हियर द बेस केस इज रॉन्ग.
तो ये हाँ ये सेम होगा, बस प्लस इक्वल टू 1 होगा.
मतलब प्लस इक्वल्स टू 1 हमेशा नहीं होगा, वो एक स्पेसिफिक केस में
हाँ,
होगा.
अगर वो दोनों बराबर हैं तो.
बराबर हैं और 0 है तो
हाँ, मतलब 0 है तो
बेसिकली उसको आप ऐसे कर सकते हो कि
अगर नम्स n -1 0 है तो 2 कर दो उसको बस.
हाँ, यहाँ पर आप उसके साथ खेल सकते हो, उसको सिंपल करना है तो ऐसे कर लो. पूरे को एल्स में डाल दो या कंटिन्यू कर दो. अब ये चल जाएगा. कूद वन एक्चुअल केस ही नहीं चला. अरे यहाँ पर ये गलत है ना, टाइप हुआ है.
सर वो कंडीशन लगा दो कि s हमेशा -1000 से 1000 के बीच में होना चाहिए.
हाँ, वो
बस
ये सम कुछ भी मतलब सम कुछ भी दे सकता है ये, बट सम ऑफ एरे उतना ही रहेगा।
हाँ।
तो उसको कंडीशन लगाना पड़ेगा वहाँ पे। हाँ, बहुत ही बेकार सा टेस्ट कैसे हो।
सबसे ऊपर सर।
अरे सम को हटा ही देते हैं ना यहाँ
यहीं पे
पर।
सीधा लगा दो सबसे ऊपर इफ एस।
सीधा -1 रिटर्न करते हैं ना, मतलब
हाँ।
0 रिटर्न करते हैं ना।
सर लेस देन -1000 भी कर दो, क्या पता
नेगेटिव।
कोई और। सर
अरे
पागल है ये, कुछ भी कर देगा।
हाँ, वो करता है। अरे यार ये है, है। अरे ये रेंज में होगा ना।
एंड
नहीं, एंड नहीं होगा, वो लेस ही होगा। वो या तो 1000 से ज़्यादा है, तो 1000 से -1000 से। देखो अभी इसको चलाते हैं, ठीक है। फिर उसके बाद सोचेंगे वो क्यों नहीं हो रहा। सम 0 के लिए अभी भी गलत आएगा वो। यार सम 0 के लिए क्यों गलत आ रहा है वो। ऑफ द बेस केस। एसेंशियली वो यहाँ पर इस केस की वजह से आपका सम 0 के लिए वो आ रहा है। अब रोएगा ये तो। अच्छा, अरे ये पता है, ठीक है। ओके, लेट्स डिबग इट एट द एंड ऑफ द क्लास, ठीक है। बहुत सारा टाइम जा रहा है। लेट्स कंटिन्यू, वी विल डिबग इट in towards the end of the class. Okay, but you got the idea, right? We will debug it. If you want to stay around and see the debugging, you can stay around. I will debug it in front of the class only, but let's not waste more time on that. Let's do this question. What do you think about this question?
Sir, we'll check that if using some elements, use some subsequence, we are able to make s by 2 the sum by 2 or no.
Yeah, isn't this the same question that we did now? where we have to form a sum of 0 by using plus and minus. Do you see that?
फिर ये तो सबसेट सम की तरह ही कर लेंगे ना,
क्या सबसेट सम?
मतलब कि पहली बात तो वो सम हमारा इवन ही होना चाहिए, तभी उसको 2 में बांट सकते हैं।
ठीक है।
और अगर और अगर कोई भी एग्जिस्ट करता है, मतलब सम बाय 2 को चेक कर लेंगे, अगर कोई भी ऐसे हैं जो सम बाय 2 सेटिस्फाई कर रहे हैं तो हाँ मतलब है वो, तो ट्रू आएगा। क्योंकि अगर कोई भी एक सबसेट, मतलब कोई भी है सबसेट जो सम बाय 2 कर रहा है, तो बचा हुआ तो सम बाय 2 करेगा, तो सम हो जाएगा ना दोनों में।
राइट। मतलब वो सबसेट कैसे करोगे? व्हाट इज द डिसीजन?
वो सर मतलब हाँ चेक कर लेंगे कि उसको ले सकते हैं या नहीं ले सकते हैं, नैपसैक की तरह ही, मतलब या तो उसे लो या फिर ना लो।
Right. You could do that decision. What I'm saying is, isn't it the same problem that we did now, wherein we have to find pluses and minuses for the numbers such that वो sum 0 हो जाए? You could do it that way, like what you are saying, I understand. So isn't it the same problem with numbers? You have some numbers, right? So isn't it the same problem as assigning plus and minus to these numbers such that the total sum becomes 0? So you have to find whether is there at least one assignment of this type. How many of you understand this? Others don't understand this. This is fairly easy, right? Intuitive also. Yeah, so you could do it this way. But I have taken this example to illustrate another decision, which is include exclude for a 2D case. So that's why we will still do this. By the way, that code ran. I will show you that code now. So this is the question. We are in the previous question. I just debugged it. So I'm just showing you. So the change that I made was here, that if you have a, so there are two cases here in the base case, just to explain you, that nums of n minus 1 could be a 0 or could be anything non-zero, right? So if it is non-zero, then basically you will have, just for that particular place, you will increment your sum to, for minus, so let's say nums of n minus 1 is 1. So for 1 and minus 1, you will make this 1, right? So that's what we are doing here, that if it is minus 1 and if it is 1, then these are the two cases. If it is 0, then we have to basically have two ways. So the initialization should be that dp of n minus 1 0 should be 2, right? So what I did was I just had 1 and I added that here, added one more here. Otherwise I just kept. So if I is 0, then what happens is this index comes out to be the same, right? Do you understand this? Another way to do it could be that you could just do a plus 1 here and a plus equals 1 here. This is also a fine. This is also fine. ठीक है, ये समझ आया? How many of you understood this question overall? Like, can you acknowledge? We can move ahead quickly. This was the issue in the code. The other way you could have done this is you could have taken your base case to be an empty row instead of taking the last row. So what you could have done there is, in the same problem, what were we doing? When we said that we will fill the last row. So just the sub problem, the smallest sub problem will be the suffix array with element 1, with just one element. I will initialize that. That would be my base case. The other way I could have done that is I could have taken an empty suffix array to be the base case, right? So then I would have created an array of dimension n plus 1 here, of size n plus 1 here. And for an empty suffix array, it is always all 0, right? No matter what the sum is, there are no ways of making that sum. Except, right? For sum 0 also, we will, for the column, for this column where the sum is 0, will this be 0 or 1 for the empty suffix array? It will still be 0, or will it be 1? Do you get the question? So there is one way of making this 1. So I could have changed this code to have an empty suffix array. So then my DP array would have become n plus 1, right? And this I don't really need to do. I could have simply done a DP of n. This represents the empty suffix array. Zero plus 2000 to be 1. So from an empty suffix array, I can only make a sum of 0. And everything else, I could then start from n minus 1 and go over all these. Right? Do you understand this even more trivial base case? So you could have optimized it in this manner. Now let me show you one more thing that you could have done here. Clear? Is this clear? Pranav, Karan, guys, is it clear? Like, I wouldn't know unless you tell me. Karan, is it making sense, the empty subarray, this as the base case? Yeah. So now let's see. Now see one more thing here through this example. When I am computing for an I am only using I plus 1. I am not using I plus 2, I plus 3, I plus 4. So what I could do is I could only keep the last row. When I'm at a given row, I can only keep the last row and I would be fine. Right? So what I could do then is I could initialize this DP vector to be of size 2. So I will just keep the current row and the last row and I will recycle. Okay, I will keep just the current row and the last row. So I will have a DP vector of size 2 and I can do a modulo here. So all the places that I wrote an I could do a modulo. So that way I could recycle. I could recycle line 13. array and so this is what we call dimensionality reduction. What we did here, I will just explain this. What we did here is, oops, sorry. So what we did here is, we said that whenever we are at a given row, we are just using the previous row's values, right? So when we are computing for this row, we are using previous row's values. So when we are here, we are using two values from here, right? So why can't I just keep a 2 by some vector, just this 2D array? And what I will do is, to start with, I will have my n here and I will be computing for n minus 1. Once I have computed for n minus 1, I can, for n minus 2, I can reuse n, right? So I can, for n minus 2, I can reuse this space and I can read the pre-computed values from n minus 1. Now, once I have at n minus 2, what I can do is I can reuse n minus 1 because n minus 1 is not needed now. So for n minus 3, I can reuse this n minus 1 space. So that's basically the idea of a modulo. I have taken a modulo so that I can reuse the previous row, which I computed for the next row computation. Do you understand this? How I reduce the dimension here, like the space requirement? Get an intuition why modulo works? I can explain again if any of you don't get the modulo thing. Karan, does this make sense? Like people who are hearing it for the first time, are you able to follow? Yeah, Kusagar, I have just, so basically we are looking at another problem of dimensionality reduction or space reduction. So we did all the analysis that we had to do for a 2D array. And we said that when I am at a given array I am using the value of I minus 1, right? Values of from I minus 1, correct? So why do I need an array of size n or n plus 1 here? Do I really need that? If I can go about doing it in this way, that I initialize a array of size 2 of 2 rows. I will use the 0th row for, I will use, let's say n is odd. I will use one of the rows for n, for this n. Now when I am at n minus 1, I can use the other row. Let's say I use this row for n. I could use this row for n minus 1 and copy and use the, when I'm computing values, I could use the values from this row. Right now, when I'm moving on to n minus 2, this row, which is the previous row, is no longer needed. I only need the results of this row, right? So I can use this particular row for computing for n minus 2. Similarly, when I am at n minus 3, now this row is redundant. So I can use this row for n minus 3. Right? So that's basically, I'm going about it in a cyclic manner. If I have n is 6, for 6, I am using the 0th row. For 5, I am using the first row. For 4th, I am using the 0th row. For 3rd, I am using the first row. For 2nd, I am using the 0th row again. Right? So it's happening alternatively. So that's basically how I can reduce the dimension. And that's what I try to show in the code here. I could just declare a DP of vector of size 2 and get away with it. I will just take a modulo everywhere. Everywhere I write an index, I will take a modulo too. Karan, did you got it? How will zero remainder work? There will only be 0 or 1 remainder, right? And I will alternate because the parity of the number changes every time. And if n is odd, n minus 1 will be even. Then n minus 2 will be odd again. Right? So when I'm computing n minus 1, I can use n. When I'm computing n minus 2, I can use n minus 1 because n minus 1's parity will be different from n minus 2's parity. Parity is basically whether it's even or no. You can just assume. So that is another aspect of dynamic programming wherein we can reduce dimensions. So you could generalize this. If you remember, for 1D cases also we did that when we were at a given index I and we wanted to compute, we were using only I minus 1. What we did was we used a single variable previous and we updated it, right? Similarly, this is the 2D analogy to dimensionality reduction. If you are using just the previous row here, you might as well get away with just using 2 rows. So that's basically dimensionality reduction for you. Now let's come to the question which we gave now, which is basically you have to find out if you can divide. You are given a set of numbers 2, 3, 5, 7, 9, 1. You have to find whether you can divide it into 2 equal sums. So how can you do that? Basically, you can find out the total sum and divide it by 2. So that is the required sum. So if you can get one subset with this sum, then you will be good, right? And how can you get one subset with this sum? What is the decision? This is a subset. So the decision could be you choose to include this or not in this subset. So if you include it, then you will be left with this particular subarray, which is a suffix array, and you have to now find rs minus 2. If you exclude it, then you will be left with this particular array and rs plus 2 or rs, sorry. You will be left with the same sum you want to form. So that is now a DP, right? Now what are the two what is the sub problem? It's a suffix array and a sum. So again, you could do a 2D DP here. With the same, everything remains the same. When you are at a given index, you are just using the previous row. If the rows are suffix arrays, if the rows represent the size of suffix arrays. So that's how you could do this question. The other way to think about the same question is, this is nothing but the previous question that we did where we have to assign plus minus to numbers such that the total sum becomes 0. That's what we have to do in this question. So it is the same question. So I just illustrated two decisions that you could do or make here. Let's take another question. Do you want to do DP? Knapsack? Yeah, let's. How many of you are familiar with Knapsack? Okay. Yeah. We're not doing knapsack. Try this question first. Yeah, we will go through knapsack. Don't worry. So think about this question. This is not so easy. So this is the same stone weight question with a little twist. And that twist is difficult to try this question, I would say. Give it a thought. This is not like you, if you think more on this, about this question, I think you will get it. Let's move on to another question. Let's try this question now. So what is the question telling you? The question is telling you that you are given an array of numbers. You are given an array of numbers 5, 4, 7, 3, 2, 9. You can use a particular number one or more times, 0 or more times actually, and you have to create a target sum. So you have to find the largest sum that is possible by using one or more of these numbers 0 or more times, which is less than equals to target. So you have to find a t which can be formed by taking elements from this 0 or more times such that t is less equals target. So for instance, if your target is 13, then let's say your target is 14. So if you pick 5, 4, and 4, you can get 13. If you pick 5, 5, 4, you can get 14. So this will be the largest sum that you can make, which is less equals 14. If you remove this 5, let's say you have another, 11, then you can make possibly 7 plus 4, 7, 4, and 3. If you take, you can make 14. So you have to find the largest sum which you can make less equals the target by taking each of these elements 0 or more times. That's the question. Now let's look at what this question is, what kind of decision we can make here, and then we will generalize it. So you have some numbers, and you have a sum S. Think about the sum. Think about the sum, the result. Result is the sum, which is the largest sum, which is less equals S, right? Think about the result. And think about the first element of that result. What can that first element be? That first element could be this, 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 could be this. Right? If that first element from the result is 5, then what are you left with? You are left with the same array again and S minus 5. If that first element is 9, you are left with S minus 9 and the same array. Right? So this decision is basically recap. If you remember in the beginning of the class, I told you there is a this decision is also very popular, which is basically look at the first element, and that first element could be any of these. So the maximum that you can make from these numbers, whatever that is, you can find out in this manner. So let's say dp of s represents the maximum you can make from these numbers, which is less equals s. So what will that be? That will be, if you choose maximum of, if you choose ai, then whatever you can make from, whatever maximum you can make from s minus ai, that plus ai, this maximum over all n, right? So this is the recurrence now for this problem. So this is a 1D DP where the dimension is only the sum. And what is the complexity? The complexity is n square. Right? Do you understand this? Guys, do you understand this? Or should I explain again? Any part of this you don't understand? This part, Akash, this part you are saying? So that part is basically, think about, so now basically what you have to do is, you want me to explain the recurrence, Karan, is it? Okay. So this is similar to palindrome partitioning or the question that we were doing. Think about the solution and think about the first element of the solution. That first element could be any of these, right? We have infinite capacities of each of them. So the first element could be anything. If the first element is 3, then what is the sub problem you are left with? You are left with the entire array. So that's not changing because you have infinite capacities of each of them. But you now have to create some s minus 3 from the same sequence. Whatever largest you can get from this array for some s minus 3, that plus 3 would be the largest that you can get for s. Right, Karan? But this is if you take 3, if 3 is the solution, but 5 can also be the solution. 7 can also be the first one. 9 can also be the first one. Any of these could be the first one. So we will take the maximum of all these. Right? So in this case, what is the sub problem? You understood why we are taking the maximum of this? Because we don't know which is the first one. Right, Karan? Do you understand why we are taking the maximum here? Okay. You understood an individual recurrence, right? That if we are taking, so here in this recurrence, what is the assumption? The assumption is that 3 is the first element of the result. Correct? But that assumption is need not be correct, right? 5 can be the first element also. 7 can be the first element also. So we are saying you can find for all possibilities. What are the possibilities? 3 can be the first element, 5 can be the first element, 7 can be the first element, 9 can be the first element. If 3 is the first element, you are left with s minus 3. And you have already created a sum of 3. If 5 is the first element, you are left with s minus 5. And you have already created 5. Right? And we have to find the largest sum that is possible, which is less equals s. So the largest sum which is possible, which is less equals s, will be the maximum of all these. So that's basically the recurrence. So in the recurrence now, what is the sub problem? The sub problem is a sum which is sum less than s. So your sub problem is a 1D sub problem, a sum. And for computing a sum, what are you doing? For a given sum, what are you doing? You're going over this array and doing this. Assuming, now think about what you are using a smaller sum to compute a bigger sum, right? You're using s minus 3, s minus 5, s minus 7, s minus 9, s minus 11, s minus 12. So these are all the smaller sums that you are using to compute this bigger sum. So you should, the order should be from the smallest sum to the biggest sum. Correct, Karan? And others? And when you are at a given sum, you will now go from the smallest to the biggest sum. So when you want to find for a particular sum, you are using previous sum values. And how many, for a given s, how many previous such sum values you are using? You are using n such previous sum values, right? You are using s minus a0, s minus a1, s minus a2, s minus a3, and so on, right? So for a given sum, you are using n time. So for all the sums, you have to compute this. So the total time will be n into s. Right, Akash? Does this make sense? What is the question, Karan? Can you unmute and speak? Maximum n? I don't know.
Sir, we have to check for maximum n times.
We have to check for maximum n times, yes. If the sum becomes negative, we can stop. It is very similar to the coin change problem, yes. What could be the, it is exactly the same as the coin change problem only, if you know the problem. What could be another way of, no, we are not assuming sorted. You can skip if the sum is negative, s minus ai is negative. That's the only point he was saying. Why is a sorted assumption needed here? Smaller to bigger sums, not the smaller to bigger array. Array is fixed here. Don't confuse between an array and a sum. You are given a target sum and an array. हाँ मतलब वही है, वो लेस इक्वल्स टारगेट इक्वल्स टू टारगेट, डिसीजन एक ही है, सब कुछ मोर ऑलमोस्ट उतना ही, वही सेम है बेसिकली. Problem is obviously different. If your point is the problem same, problem is different. Solution is almost the same. Like the decision and the DP, the space. Ayush, did you understand? Here we are, our DP variable is the sum, not the array. Because the array is not changing. How many of you understood this decision? So this is, if you really think deep, this is the same decision that we made for palindrome partitioning or the word break problem. The same decision. These are all similar decisions. In word break, the decision that we were making was, where do we place the first partition? So basically, our solution was a set of partitions. You could think about the solution, abstract the solution of a word break problem as indices of these partitions. Let's say if you are placing this after index 2, and if you are placing another one after index 5, then let's say your word break solution, you can abstract it to be 2 5. 10 बज गए क्या? हाँ मैं मीटिंग चालू कर देता हूँ, 5 मिनट तो ऐसे ही वो लोग बकचोदी करते हैं. ठीक है, मीटिंग तो चल रहा है. So the word break problem can be abstracted to this, right? Which is the index of the partitions. And then what are we saying? We are saying that we are finding the first element of the solution. That could be index 0, that could be index 1, that could be index 2. If it is index 2, then we are left with us. The only difference was we were being left with a smaller instance of the array. And here we are left with the entire array again. Correct? So the decision is roughly similar. Another way you could do the same question is, there is another way you could do the same question. Can anyone tell me another decision basically? So for that decision, think about, use the decision that we have been making. Think about the decision on this. Yeah, include, exclude. How? You have a given sum S. So you can either choose to include it 0 times or more than 1 time, more than 0 times. If you are including it 0 times, then your problem becomes S, the sum itself, and this array. Correct? And if you are including it more than at least 1 time, then your problem then becomes this entire array and S minus A0. Correct? Did you follow this decision? Because it's a 0 or more times, you can take this any number of times. If there was a constraint that you can take it only 1 time, at most 1 time, then here also your subproblem would become this. But because you can take it many number of times, your subproblem becomes this and S minus A0. So now you have a 2D DP here. You have a sum as one of the dimensions and a suffix array as another dimension. And if you see, mute kar diya. So now, and if you see, here also you are basically filling from smaller suffix arrays to bigger suffix arrays. So you can again do the row wise filling if you are going with this decision. So 2 types of decisions we said. We said look at the solution, the first element of the solution, and make a decision on that. The decision is the same, first element of the solution. And the other is you can choose to include, exclude. So these are the type of decisions that can enable you to solve this question. Right? So the modified version of this question is, if you are given an array and a sum, and you can take an element exactly at most 1 time. What is the maximum sum less equals S that you can form? So then the problem is, you can either include it or exclude it. If you exclude it, then you are left with some S and this part of the array. If you include it, then you are left with some S minus A0 and this part of the array. Right? Does everyone understand both the decisions as well as this modified version of the problem, the decision for that? This is final set of acknowledgements. Just one more time you have to type yes. After that, you don't have to for today. Okay, so try this. So try this question at your home and see if you can code it. So this is nothing but, I will talk about it in detail tomorrow. This problem is called an unbounded knapsack. And this is called a bounded knapsack. We will formally define the knapsack problem tomorrow, but this is basically essentially the knapsack problem. So you could do it with 1D dp n square, or you could do it with 2D dp n square. Both are fine. Okay, so give it a try, and we will continue from here tomorrow. We will look at other ways of filling the matrix. We will look at diagonal filling when we take longest common subsequence or edit distance. So we will look at those problems also tomorrow. All 2D DP tomorrow. हाँ मैं related questions की link भेज दूँगा. ठीक है? So try this knapsack, this question. Maybe make sure you understand this matrix tomorrow. This matrix, all the nitty-gritty of this, the dimensionality reduction, the order. We will just use all of this tomorrow again.
They cannot lock down forever, right? I mean, government cannot even run.
Okay. So try this, and we will continue tomorrow from here. I will, if you have questions, I can wait for a minute or so. Or otherwise, thank you for joining. I will see you guys tomorrow. I will end the meeting.
It's not like supermarket everywhere here, right? So we have local shops as well. So I mean, how
All right.
far can they
Thank you guys. Good night.
keep the social distancing? Difficult, but to certain extent they are supposed to follow. Certain times they are following. But if you